Welcome to RoRe Academy YouTube channel 2.0. Our new and improved channel is dedicated to showing you how things are put together, from concept to prototype. Welcome to RoRe Academy. In today's video, we begin a detailed teardown and technical analysis of the BYD Seal Power Domain Controller, focusing on how BYD has architected and integrated the core power electronics that drive this next-generation electric vehicle. This is part 1 of our deep dive series where we'll explore the system-level design philosophy, functional partitioning, and the role of the power domain controller in managing energy flow between the battery, inverter, auxiliary loads, and vehicle subsystems. We'll break down the hardware architecture, discuss key power semiconductor choices, thermal considerations, and control integration, all from an engineering perspective. This analysis is aimed at EV engineers, power electronics designers, researchers, and anyone who wants to truly understand how modern electric vehicles are built from the inside out. The BYD Seal is an all-wheel drive, battery electric passenger vehicle capable of accelerating from 0 to 100 kilometers per hour in just 3.8 seconds, placing it firmly in the high-performance EV category. In terms of efficiency and real-world usability, the BYD Seal delivers an estimated driving range of approximately 570 kilometers, based on a combination of low-speed city and high-speed highway test cycles. This performance is supported by a substantial 82.5 kilowatt-hour battery pack, providing a strong balance between power delivery, energy density, and long-distance capability. From an EV engineering standpoint, high-speed charging is not a limitation for the BYD Seal. The vehicle supports up to 150 kilowatts kW DC fast charging, enabling a charge window from 30% to 80% state of charge in approximately 26 minutes. This aligns well with optimal battery thermal management and charging curve efficiency, minimizing degradation while maximizing turnaround time. For daily usage, the 11 kilowatts onboard AC charger allows efficient level 2 charging at home or at the workplace, delivering predictable overnight replenishment with minimal infrastructure requirements. The combination of high-power DC charging and robust AC capability makes the BYD Seal well-suited for both long-distance travel and everyday operation. At the heart of the BYD Seal powertrain is its advanced 8-in-1 power domain controller. This integrated unit serves as the central nervous system of the vehicle, delivering a peak power output of 235 kilowatts and handling peak currents of up to 550 amperes. Supported by an efficient water cooling system for thermal stability under high load. What makes this architecture particularly significant is the level of integration. The power domain controller consolidates the vehicle control unit, battery management system, power distribution unit, DC-DC converter, onboard charger, and traction inverter into a single, tightly integrated module. This high level of functional integration reduces system complexity, improves efficiency, enhances thermal management, and enables faster control response. All key enablers for high-performance, high-reliability electric vehicles. A quick teardown and disassembly of the power domain controller reveals the key hardware that enables high-performance operation. Inside the unit, we can identify several critical components, including the output current sensor module, DC-link capacitor module, a high-power fuse, 2 high-voltage power relays, a silicon carbide power module, and a dedicated DC current sensor. Each of these components plays a vital role in managing high voltage, high current, and fast switching transitions, ensuring efficient energy conversion, accurate current measurement, and robust system protection under all operating conditions. In this section of the video, we disassemble the onboard charger and DC-DC converter power board, revealing its modular internal structure. The assembly is divided into 4 distinct subboards, each serving a specific function within the power conversion system. The first subboard handles the onboard charger control, managing charging logic and communication. The second subboard is dedicated to electromagnetic interference, or EMI mitigation, ensuring compliance with automotive EMC requirements. The third subboard provides the low-voltage power supply, supporting auxiliary electronics and control circuits. And the fourth subboard is responsible for DC-DC converter control, regulating high voltage to low voltage power conversion. This modular design improves serviceability, noise control, and functional isolation, while supporting high efficiency and reliable operation. The remaining printed circuit boards within the power domain controller complete the core control and sensing architecture of the system. These include the inverter control board, the main processing board, the three-phase current sensor board, the DC current sensor board, and the low-voltage filter board. Together, these boards handle real-time control, signal processing, current measurement, and noise filtering, enabling precise inverter operation, accurate power monitoring, and stable low-voltage supply across the entire powertrain. In Part 2 of our BYD Seal Power Domain Controller Teardown series, we shift our focus to the traction inverter, the core power electronic subsystem responsible for converting DC energy from the battery into three-phase AC power for the electric drive motors. In this video, we take a close look at the inverter structure, examining how BYD has implemented a high-power, silicon carbide-based inverter within its integrated power domain controller. We'll analyze the power module layout, DC link architecture, current sensing strategy, and gate drive and control interfaces that enable high-efficiency, fast switching, and precise torque control. From semiconductor selection and thermal design to packaging and electromagnetic performance, this teardown provides insight into the engineering trade-offs behind a modern, production-ready EV inverter. This analysis is intended for EV engineers, power electronics designers, researchers, and students who want to understand how real-world electric vehicle inverters are designed, integrated, and optimized. Let's begin Part 2 of the BYD Seal Power Domain Controller Teardown with a deep dive into the inverter architecture. In Part 1 of this series, we disassembled the power domain controller to identify its key internal hardware. This included the output current sensor module, DC link capacitor module, a high-power fuse, two high-voltage power relays, a silicon carbide power module, and a dedicated DC current sensor. Each of these components plays a critical role in handling high voltage, high current, and fast switching transitions, ensuring efficient energy conversion, accurate current measurement, and robust system protection across all operating conditions. In this part of the series, we turn our attention to the core elements of the BYD Seal Traction Inverter. We begin with a detailed discussion of the inverter control board, examining how BYD implements real-time control, sensing, and protection to achieve precise motor torque control and high system efficiency. We then take a close look at the silicon carbide power module used in the inverter, analyzing why SiC devices are selected for this application, how they enable higher switching frequencies, lower losses, and increased power density, and how they are integrated from both an electrical and thermal perspective. Finally, we examine the DC link capacitor module, discussing its role in voltage stabilization, ripple current handling, and transient performance, as well as the design trade-offs involved in selecting capacitors for high-power automotive inverters. Together, these elements form the foundation of the BYD Seal's inverter architecture, and understanding how they interact provides valuable insight into the engineering decisions behind a modern, production-ready electric vehicle powertrain. The BYD Silicon Carbide Power Module, BM840F12B34U2, is designed to deliver low switching losses, enabled by BYD's advanced SiC MOSFET chip technology. This makes the module well-suited for high-performance traction inverter applications, operating efficiently across a switching frequency range of approximately 1 to 30 kHz. In this section, we also examine the internal device structure. You can see the die cross-section SEM images, along with the optical views of the die layout and the die cross-section in optical microscopy. These images provide insight into the device architecture, layer structure, and packaging approach that contribute to the module's electrical and thermal performance. The BYD Silicon Carbide Power Module, BM840F12B34U2, is rated for a drain source voltage of 1200 volts and a nominal drain current of 500 amperes, making it suitable for high-power electric vehicle traction inverter applications. The module operates with a gate source voltage range of -5 volts to +18 volts, enabling robust gate control, fast switching performance, and reliable operation under demanding high voltage and high current conditions. Here, we can see the package outline of the BYD Silicon Carbide Power Module, BM840F12B34U2. The layout clearly highlights the three-phase inverter structure, with the positive and negative DC terminals, P and N, prominently identified. This module integrates a complete three-phase power stage, specifically designed for electric vehicle traction inverters, enabling compact packaging, low parasitic inductance, and high-efficiency power conversion under high voltage and high current operation. Shown here is the traction inverter section of the BYD Seal Power Domain Controller, alongside its equivalent circuit diagram. The inverter is implemented as a three-phase, two-level voltage source inverter, which converts the high-voltage DC from the traction battery into a controlled three-phase AC supply for the electric motor. At the heart of the traction inverter is the DC link capacitor module, a critical component responsible for stabilizing the DC bus voltage, absorbing high-frequency ripple currents, and minimizing voltage overshoot during fast switching transitions. This ensures stable inverter operation under high load and high switching frequency conditions. Power conversion is handled by the BYD Silicon Carbide Power Module, BM840F12B34U2, which integrates the three-phase switching stage using advanced SiC MOSFET technology. Mounted directly on top of the power module is the inverter control PCB, providing gate driving, protection, and real-time control while minimizing parasitic inductance and improving switching performance. Finally, the output of the three-phase traction inverter is monitored using a dedicated output current sensor, enabling precise current measurement for torque control, efficiency optimization, and functional safety. Together, these elements form a highly integrated, high-performance traction inverter optimized for modern electric vehicle applications. In Part 3 of our BYD Seal Power Domain Controller Teardown series, we shift our focus to the onboard charger, taking a closer look at its structure, layout, and integration within the PDC. The onboard charger plays a critical role in converting AC grid power into regulated DC energy for battery charging. In the BYD Seal, this function is fully integrated into the power domain controller, contributing to the system's high level of power density and functional consolidation. In this section, we'll examine how the onboard charger is partitioned mechanically and electrically, including the power stage arrangement, control and gate drive circuitry, isolation boundaries, and thermal interfaces. We'll also look at how the charger interfaces with the AC charging input, high-voltage battery system, cooling loop, and vehicle communication networks, and how these connections influence efficiency, EMI performance, and serviceability. By understanding the onboard charger structure, we can better appreciate the engineering trade-offs BYD has made between integration, performance, and thermal management. Let's start by breaking down the physical architecture of the onboard charger inside the PDC. One of the key highlights of the BYD Seal is its highly integrated electric drive unit, or EDU. This EDU brings together 8 major subsystems into a compact, vehicle-level powertrain architecture, designed to improve efficiency, reduce cabling, and simplify system integration. At the heart of this EDU is the Powertrain Domain Controller, or PDC, which alone integrates 6 critical power electronics and control functions. First is the motor control unit, or traction inverter. This inverter delivers up to 230 kilowatts of peak power and is built using silicon carbide MOSFET technology. The use of SiC devices enables higher switching frequencies, reduced losses, and improved thermal performance. In this architecture, the inverter operates alongside the e-motor to support the transition from a 400-volt battery system toward an effective 800-volt drive capability, improving efficiency during high-power operation. Next is the onboard charger. The BYD Seal supports 11 kilowatts of AC charging and up to 150 kilowatts of DC fast charging. The system also enables vehicle-to-load functionality, delivering up to 3 kilowatts to external loads, turning the vehicle into a mobile power source. The third component is the power distribution unit. This manages high-voltage power routing between the charging port, traction inverter, e-motor, and high-voltage battery pack, acting as the electrical backbone of the vehicle's high-voltage system. The fourth element is the DC/DC converter, responsible for stepping down high-voltage battery power to support the vehicle's low-voltage electrical systems, ensuring stable operation of auxiliaries and control electronics. Integrated alongside this is the battery management system. The BMS continuously monitors cell voltages, temperatures, and currents, ensuring safe operation, optimal performance, and battery longevity. Finally, the vehicle control unit coordinates all of these subsystems. It manages torque requests, energy flow, charging modes, and safety functions, effectively acting as the supervisory brain of the entire powertrain. Outside the PDC, the EDU also incorporates the electric motor and gearbox, completing a tightly integrated drive unit designed for high efficiency, high power density, and reduced system complexity. This level of integration represents a significant shift in modern EV powertrain design, and in this video we'll break down exactly how BYD has engineered it. We focus on the onboard charger in this video. Let's take a quick system-level view of the powertrain domain controller, focusing specifically on the top and bottom sections and the external connection points, without diving into internal circuitry just yet. Starting with the topmost section of the PDC, this is where most of the high-level interfaces are located. Here, we can see the high-voltage battery connection, which links the PDC directly to the vehicle's main battery pack and serves as the primary energy input for the entire powertrain. Adjacent to this are the coolant connections, which form part of the thermal management loop. These interfaces allow heat to be extracted from high-power components such as the inverter, DC/DC converter, and onboard charger. We also see the DC fast charging connection, which routes high-power DC energy directly into the system during rapid charging events, bypassing the onboard AC charger. Alongside this is the AC charging connection, used during conventional AC charging, where the onboard charger inside the PDC processes grid power. Moving to the low-voltage interfaces, the 12-volt connection supplies power to vehicle auxiliaries and control systems, typically via the internal DC/DC converter. Finally, the communication connections are located here as well. These interfaces handle data exchange between the PDC and the rest of the vehicle, enabling control, diagnostics, and safety monitoring. Now, shifting to the bottom section of the powertrain domain controller, we primarily see the e-motor connection. This is the high-power three-phase output from the traction inverter, delivering controlled electrical energy directly to the electric motor. In this section of the video, we disassemble the onboard charger and DC-DC converter power board, revealing its modular internal structure. The assembly is divided into 4 distinct subboards, each serving a specific function within the power conversion system. The first subboard handles the onboard charger control, managing charging logic and communication. The second subboard is dedicated to electromagnetic interference, or EMI mitigation, ensuring compliance with automotive EMC requirements. The third subboard provides the low-voltage power supply, supporting auxiliary electronics and control circuits. And the fourth subboard is responsible for DC-DC converter control, regulating high-voltage to low-voltage power conversion. This modular design improves serviceability, noise control, and functional isolation, while supporting high efficiency and reliable operation. If you found this video insightful, don't forget to like, subscribe, turn on notifications, comment, and share, so you never miss our next deep dive into the world of technology and innovation.